Let me begin by asking you this question. So, question. How many different ways are there to order a sandwich at Subway? Do you know we have a Subway store in this campus, right? Yeah, I often go there. Today, as a matter of fact, I went there and then got a sandwich. So how many different ways are there to order a sandwich there? So have you been there or tried ordering a sandwich? Usually, if you go to a Subway, then you have to choose bread, right? So choose bread. I don't know exactly how many possibilities, but let's say 10. There are quite a number of ways to choose bread. And you decide size, maybe 15 centimeter or 30 centimeters. So there are two possibilities for the size, and for the meat, I don't know exactly, but there are many. Yeah, I wrote 30, but is that many? I'm not sure. But let's say there are 30 possibilities to order the meat. I think it's less than 30. And vegetables, and you can choose. You can select this, or you don't want. If you don't want onions, you can say, "Oh, I don't want onions," or peppers, pickles. I don't want that. Something like that. So for vegetables, let's say there are 10 different vegetables, and then for each vegetable you can either say, I want this or not. It's two possibilities for each. So 2 to the 10. And you can choose sauce, dressing, and I think you can choose up to 2, but let's say there are 20 in total. So you have to make a choice at each stage, right? You have to make this choice for your bread and the size and this and this and this. Right? And total, what is the total? We just multiply all of this, right? If you multiply 10 times 2 times 30, 2 to the 10, 20, and this is approximately 12 million ways. There are many. So I think if you go there every day, different choices every day, then, but still, I don't think you can. I think you can go there for the rest of your life, having different choices. So this is an example of a multiplication principle. So let me state the principle, but I think it's not really necessary to write this down, but let me do this. You basically know, like I did, multiplication. You somehow know this, although you may not have noticed that it's called multiplication principle because it's too simple. So like the example that I showed you, an activity is constructed in L successive ways. Where in the L steps. So step 1 is done in, say, N1 ways. So step 2, there are L steps. Step 2 is done in N2 ways, etc. So step L, the last step, is done in NL ways. Then the number of different activities is the product of this. It's a multiplication rule or multiplication principle. The thing is, you have to do this. You have to do all these steps: step 1, and then step 2, step 3, etc. then you get this number. So like a Subway sandwich problem. And another example would be something like this. Actually, I implicitly use this fact, but let's prove this. Number of subsets of this 1, 2, 3, n element set. What is the number of subsets of this? Okay. So we can construct a subset by deciding whether 1 is in the set or not, and 2 is in the set or not, etc. So a subset is of n, 1 to up to n. A subset is constructed by choosing like whether 1 is in the subset or not. Here we have two possibilities. And 2 is in the subset or not, two possibilities, etc. The last one is in the subset, two ways. For each step, we have two choices, whether this element is in the set or is not in the set. So if you do all of this, if you complete all of these steps, so it's like a yes or no question. Is 1 in there? Is 2 in there? Etc. If you have answered all of these n questions, then you will create a subset uniquely. So this 2 to the n is the number of subsets. So the answer is 2 to the n. We already know this, but it can be explained using multiplication principle like this. Okay, maybe you can see more or less known problem. So number of pairs A comma B, number of pairs of subsets, not just the number of subsets, but number of pairs of subsets of, say, 1 to ... n. Let's say x. Pairs of subset x, which is the set of elements 1 to up to n, such that A is a subset of B. Now, if you don't have any conditions on A and B, then of course number of pairs of subsets will be 2 to the n times 2 to the n, which is 4 to the n. Okay? But we have this condition. So, solution. So A is a subset of B. And of course B is a subset of X. So we can consider the Venn diagram. So X is here, and B is a bigger set. A is a smaller set, like that. So a Venn diagram will be drawn like this, okay? Because A is a subset of B. Now, there are three regions. Region for A, B minus A, X minus B. And for each element, 1, 2, 3, up to n, we have three choices. We can put that in this region, or this region, or this region. Okay? For each element, say I in X, we have three choices. The choices to place I into one of the regions, into the three regions. One of the three regions. Here, or here, or here. Okay? They all give you different pairs, A and B and C. A comma B. So for one, so step 1 is place 1 in one of these regions. Step 2, place 2 into one of these regions, etc. So what is the answer then? In each step, there are three possibilities, and of course there are n steps, so it's 3 to the n. Okay, so it's pretty easy. If you want to compare this with the previous problem, then in the previous problem we have only x and A. So for each element I, we have two choices: either place that element here or here. So it's basically in that sense that they are quite similar. Okay. So this is the multiplication principle, and a counterpart of this is addition principle. So addition principle is like this. It's even simpler. X1 to XL, these are pairwise disjoint set. So any two of them, if it intersect, it'll be the empty set. Then let's say the ith set xi has cardinality ni. Then number of ways to select one element from one of these sets L is n1 plus n2 plus, instead of multiplying them, this cardinality we just add them. So in other words, a quite trivial thing, but in other words, the cardinality of x1 intersect union xl is the cardinality of x1 plus dot 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 xl if they are pairwise disjoint. Yeah, it's pretty obvious, right? They don't have anything in common, so yeah, it must be the case. So the difference between multiplication principle and addition principle is that for multiplication principle we have different steps and we have to do each step. But here there are L sets, but we just select one of them, not all of them. Just one, select one, and then select one element from there. So there's only one step in that sense. We do just one thing. We just select one element. Not one element from each set, just one of them. Okay, so an example. What can I say? Number of ways to take two classes of different fields. Where among, say, 5 distinct courses from computer science and, say, 4 distinct courses from math and 3 different courses from physics, say. Then what is the number of ways to do this? We want to take 2 courses, but different fields, meaning different majors. So there are several ways. Select one from CS, and one from, say, math. How can we do this? We do so one step is to select one element from CS, so one course from CS, so that's 5, and one course from math, that's 4. And we multiply them because we do this at the same time. Or select one from CS and one from physics. It's going to be 5 times 3, or select one from math and one from physics, 5 times 4 times 3. So we can do either this or this or this. Okay? So the answer will be sum of this. 5 times 4. So it's kind of mixed. So we use both multiplication rule and addition rule. Multiplication rule is used to compute this, and addition rule was used to compute this. Okay. So these are very fundamental principles, so we will use this very often. But they are very simple, so yeah, it's easy to remember. So we will learn, so in this section, we will learn several principles to count the things. And, in this addition principle, this allows us to compute the cardinality of the union of several sets. If they are mutually, or this pairwise disjoint is very easy. But in general, if you have many sets, they may have some intersection. How can you compute this when there are intersections? And this is principle of inclusion exclusion. So inclusion exclusion principle. Okay. For the small number of sets, you have already seen this. So for finite sets, say x and y, the cardinality of x union y is equal to x plus y minus x intersect y. Okay, we know this. If they are disjoint, then because this is 0, is sum of this and this. And for a finite sets x and y and z, we can have similar formula. The intersection, the cardinality of the union x, y, z is you add cardinality of one set, and then you subtract the cardinality of the intersections of two sets, or possible intersections of two sets, like this. And then we add the intersection of three sets, all possible intersections of three sets, which is only one in this case. And similarly, it has a general formula. When there are n sets, we can do a similar thing. In general, what is this? So we need to. Idea is similar. Here you can see you take the sum of the cardinalities of one set, and you subtract some of the the cardinality of intersection of two sets, and then plus and the intersections of three sets, etc. So first we add the cardinality, the individual cardinalities like this. We add this, and then minus x1 intersect x2, x1 intersect x3, all possible intersections of two sets. There are many things like this. All intersections of two sets, and plus. So here is all of xi, j, for different I and j. Yes. And plus x1 intersect x2 intersect x3, all possible intersections of three sets. Oh, there are many. n minus 2, n minus 1, x, and so all possible, and minus and etc. And at the end we get n minus 1, x1 intersect xn. Okay, so here, this is the same. All possible intersections of one set. For intersection of one set is just itself. All xi here, all xi intersect xj. Here, all xi intersect xj intersect xk, etc. Like that. And then the signs are alternating, like plus minus, like so. Yeah. I'm not going to prove this, but this can be proved using induction on n. We know these two things. These two can be seen very easily if you draw this Venn diagram. A. Okay, we don't need the x, y, then it's like that. And for x, y, z, you can consider the Venn diagram, and then it'll be done. This can be proved by induction, like I said. So this is very useful because many things can be, it has many applications. So let me give you an example using, can be solved by inclusion, exclusion. So number of integers relatively prime to 6 in is set 1, 2, dot, 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 100. What is the number of relative prime? What is the number of integers relative prime to 6? Here, relative prime means two integers, a and b, are relative prime. That means their GCD equals 1. They don't have any common divisor except 1. Okay, so let's say A equals the set of multiples of 2. So if, 6 is 2 times 3. So any multiple of 2 is not going to be relatively prime to 6. And similarly, any multiple of 3 is not relatively prime to 6. So we will consider multiples of 2 and 3 in this set. And let's say B is a set of multiples of 3 in this. Then and U is this, let's say, the universe set. Okay. Then what is the answer? An integer is relatively prime 6 if it is neither a multiple of 2 nor a multiple of 3, right? So it will be U minus A intersect A union B. These are the integers which are not relatively prime to 6. So if you remove these, then you will get the integers relatively prime to 6. So that means now we can use the principle of inclusion exclusion. We can rewrite this as follows. This is better because what is A intersect B? So this is the set of integers which are both multiples of 2 and 3. That means it's going to be a multiple of 6. So this is basically number of multiples of 6 in the universe set, 1 up to 6, 100. But number of multiples of something, number of multiples is easier to compute because we only need to do is the division. So what is the cardinality of U? It's of course 100. Cardinality of A, this is the number of multiples of 2 in integer 1 up to 100, which is 100 over 2 floor, which is 50. And this is number of multiples of 3. So it's 100 over 3 floor. And this is a number of multiples of 6. So 100 over 6 floor. Then you know how to compute this. You get 67. So we use the inclusion exclusion principle because these are easier to compute than this. Here, this at first sight this may look strange because it may seem that we make things more complicated because here we had only one, but here we have 3 things. But although we have more sets to compute, they are easier. Each of them is easier to compute. This is why we use the principle of inclusion exclusion. fun. 6.2 permutation and combinations. So what is a permutation? A permutation is permutation of elements x1 dot 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 xn is nothing but an arrangement of this. It's just an arrangement of them. You know, we just arrange them in a row. Very, very simple. So, for example, there are 6 permutations of ABC, because we can write ABC or ACB or BAC, BCA, CAB, CBA. So these are all permutations of ABC. You just arrange them. And in general, number of permutations of n element is very easy. Very nice, simple formula. There are n factorial permutations of n elements. Proof. Yeah, proof is also easy. We can use the multiplication principle. So just consider how we can construct a permutation out of n elements. So let's say pi is pi 1, pi 2 be a permutation of n elements, say x1 dot 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 xn. How can we construct such a permutation? The first letter, we have to decide the first letter and the second letter, etc. So number of choices for the first letter. Here, this can be any of this because we just arrange them. So it's n. There are n ways to do this. Either pi 1 can be either 1, 2, x1, x2, x3, or xn. So there are n choices. What about the choices for pi 2? But now pi 1 is fixed. Once pi 1 is fixed, how many possibilities are there to determine pi 2? We are not allowed to use the letter for pi 1 because they are all distinct. So we have n, there are n letters available except pi 1. So it's going to be -1. And number of choices for pi 3, now 2 elements are already used, so they are not available, so it's n-2. Dot, dot, dot. So the last one, actually there is only one possibility for the last one because, you know, n-1. Because n-1 letters have been already used, we have only one choice left. And we have to make a choice at each step, one by one like that. So the number of permutations will be the product of this, which is, of course, n factorial. Okay? So there are n factorial permutations of n letters. Using this fact, you can compute more complicated question, like this. What is the number of permutations of 1 dot 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 9? But of course, this will be 9 factorial. But we want to put more conditions. Number of permutations of 1 up to 9, in which 6 and 8 are adjacent. Adjacent means they are next to each other, either 6, 8 or 8, 6. So the solution here we must have either 6, 8 or 8, 6. They must be attached like this, next to each other, 6 or 8. So let's say x equals 6, 8 or 8, 6. Suppose x is fixed, like 6, 8 or 8, 6. Think of them two letters as just one letter, x. Then the answer will be number of permutations of elements. Permutations of like 1 up to 9 minus 6, 8. We remove this and add x, right? And of course, times number of choices for x. Because we have two choices for x too. X is either 6, 8 or 8, 6. And once we decide x, then we just permute the letters. So in other words, this means 1, 2, 6 and 8 are missing, so like 5 and then 7 and then 9, right? And x. How many elements are there here? 8. So number of permutations of these are 8 letters, so 8 factorial. And number of choices for 2 is 2. This is it. Okay, and then we will consider the permutation of some elements. We just use all of these elements, but sometimes we want to use just some of the elements, not all of them. So let me define R permutation. So on R permutation of x1 dot 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 xn is an arrangement of the elements in an R subset of this. Here, R subset means a subset which has exactly R elements. So, in other words, you select R elements from here, and then you arrange the selected elements. Okay, that gives you an R permutation. So, for example, two permutations of 1, 2, 3, 4. They are, 4 letters. 1, 2, 3, 4. How many are like this? 1, 2, it can be 1, 2, or 2, 1, 2, 3, 3, 2. I'm just listing some random 4, 2, 1, 3. There are many. So these are examples of two permutations. You select 2 of them and then arrange them. Okay? So the natural question, of course, here is how many R permutations are there? Okay. Now, by the way, just the permutation is on R permutation. So here, N permutation. Here, note a permutation is equal to. Okay. Permutation means N permutation, right? If there are N elements, N permutation is the same as just the permutation if there are N elements, right? Because you select all of them, just list them all, arrange them all. So it's a permutation. All right. So the question is a theorem. Number of R permutations of x1 N elements is. This is denoted by this letter, P of N comma R, and this is n times n minus 1 times dot 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 n minus r plus 1, which is n factorial divided by n minus r factorial. So this is the number of r permutations of n elements. Okay? Proof is similar. Basically, it's almost the same, except we stop before the nth step. So let pi 1 dot 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 pi r be an r permutation. Because we have only r elements, we have index up to 1 up to r. Now we can create such an r permutation by choosing one letter at a time. So number of choices for pi 1 is what? Every letter is available, so n. There are n choices. But once pi 1 is fixed, number of choices for pi 2 is n minus 1 because pi 1 is no longer available, etc. What is the choices? Number of choices for last element, pi sub r, is n minus r plus 1. And then if you multiply them all using this multiplication principle, you get this number. And that is, of course, equal to n factorial divided by n minus r factorial. Okay? So, yeah, this is simple. So, shall we see an example? So, number of ways to make a waiting list for 3 men and 3 women, such that no 2 men are adjacent. What is the number of ways to do this? There are 11 people, 3 of them are men, 8 of them are women. We want to list them, we want to arrange them so that no 2 men are adjacent. So, you can think of a way to construct such a list. So, for problems like this, there are many possible solutions. So this is one of them. Let's arrange the 8 women in, how many different ways are there to arrange 8 people? Just permutation of 8, so it's 8 factorial. There are this many ways to arrange women's first. And then, so let's say these are the list of women's arranged in a row. Now we can kind of put 3 men between the women over here. But because we want that no 2 men are adjacent, we cannot place 2 men between 2 women. So here only one possible. We can only put 1 man. Okay, so we need to, so here, how many positions are there? Because here, this is also position, so there are 9 positions. And then we need to place 3 men there. So this is exactly, so let's say these positions are, let's name these positions, like P1 position, the first one position, the second position, etc. 9 like that. And we have three men, like say ABC. Let's say ABC, the 3 men. We need to assign a position for A, position for B, position for for C. What is that? That means you just this is going to be pi, this is going to be pj, this is going to be pk for different ijk. This is exactly 3 permutation of these positions, right? So once you give 3 permutation, that determines a way to place 3 men. So this is exactly P, this number, 9, 3. Among 9 placement positions, we select 3 and arrange them like this. So the answer is going to be, we first arrange the 8 women in 8 factorial ways, and then we need to arrange men between women like this. This is the answer. But we have a formula for this. It's 8 factorial, 9 factorial over 9 minus 3 factorial, which is 6 factorial. Or if you want this, you can cancel this. So it's 7 times 8 times 9 factorial. Okay? All right. Okay, then I'm going to define another object, also very common, like permutation. On R combination of a set X is nothing but an R subset of X. So R combination means R subset. So here, so basically it means, so it is a selection of R elements without ordering. Ordering them. So R permutation basically means we select R elements and then we arrange them. But R combination, we just select R elements, but we don't arrange them. We just there, without considering the order. Okay? And the number of R combinations of an n element set is denoted by this. And we read this as n choose R. So here it is n choose R. Or C of n comma R. I think it is written in the textbook like this. Or maybe in your high school you have learned this as like this. Maybe you are more familiar with this notation. But these are also used very often. Okay, sometimes I will use this or this or this, but mostly I think I will use this because I think this is used very commonly in mathematics. Okay, so example. 2 combinations of 1, 2, 3, 4. We just select 2 elements from here. It's a subset, so 1, 2. 1, 3. But for simplicity, I'm going to, without these parent curly brace, I'm going to just write 1 to 4 or something like that. So this means 1, 4 set. 2, 3, 2, 4, and 3, 4. So these are all 2 combinations of 1, 2, 3, 4. Okay? So what is 4 choose 2 then? We have 1, 2, 3, 4, 5, 6 is going to be 6. Okay? But the natural question here, what is this number? How can you find this number in general? There is a nice formula for this. So theorem, n choose R is equal to n factorial divided by R factorial n minus R factorial. For where R is from 0 to n. If R is outside this range, it's just 0. by definition, because how can you select, say, 10 elements out of 5, right? So this only makes sense when R is in the correct range, meaning between 0 and n. So let's prove this. So if the cardinality of x is n, then what is the R permutation? So R permutation of x is, so R permutation means we select R elements and we arrange them. So our permutation is obtained from an R combination by arranging them. Arranging the elements there. So it's obtained in 2 steps. First, select R elements, and second, arrange them in this set, R elements. That means number of R permutations, which is P of n comma R, this is obtained, this is equal to n choose R. We first select one R combination, and then we arrange the elements in the set, in the subset. There are R elements, so the number of ways to arrange them is R factorial. So we obtain a formula, an equation like this, and if you divide both sides by R factorial, we get P and R factorial, but we know that this is equal to n factorial divided by n minus R factorial, we get the formula like that, okay? So this is the proof. So by finding, we prove this by finding a relation between number of R permutations and the number of R combinations. And because we already know that the number of R permutation is like this, then that's it. So note, if R is greater than n, then n choose R is 0. Okay? Because number of R subsets of n is 0. You cannot have a subset which is bigger than the original set. So this number, it has a special name. It's called a binomial coefficient. And we will see why it's called like that later. And there are many objects which are counted by this number. So let me give you that example. Theorem. This number, n choose R, is counted as computed is equal to one. The following numbers. So first, they're all equal numbers. Number of R subsets or combinations of n element set, right? This is true by definition because it is defined this way, all right? And also, second, number of binary sequences of length n with binary sequence means a sequence of ones and zeros. It only consists of ones and zeros. With exactly R ones, let's say, n, because the length means the number of letters there or numbers there, so it's n minus R zeros. And third, number of shortest path from 0, 0 to n minus r, r in this xy grid. Let me explain this. Let me prove this. So first is by definition, true by definition. All right. Second, I'm going to, because we know that n choose r is the number 1, we will show this by finding a bijection between these R subsets and binary sequences. So R subset, we will find a one-to-one correspondence between these and binary sequences, satisfying this relation. Okay? But if there is a bijection between two sets, then of course their cardinalities are the same. So suppose we have a set A, then I'm going to define a sequence of length n, binary sequence, as follows. AI equals, because it's a binary sequence, is a 0 or 1. This is 1 if I is in A and 0 otherwise. So for example, if we have three subsets, if you have a three subset of 5, for example, 1, 2, 3, 4, 5, 2, 3, 5, this is a three subset of 1, 2, 3, 4, 5, okay? Then this corresponds to sequence. So let me write down the positions, 1, 2, 3, 4, 5, just to make this clear. So 1 is 1 in this set? No, so write down 0 in the first position. 2 is in the set, so write 1 in the second position. 3 is in the set, so write 3 in that position. 4 is not there, so it's write 0 there. 5 is in the set, so write 0, like that. This is clearly a one-to-one correspondence. If you know this, you can immediately see that the subset is this. Okay, so one-to-one bijection. The number of ones is, of course, number of elements here, which is r. So number of ones equals r. Number of zeros equals n minus r, of course. Okay, so this proves that this is also equal to the number of binary sequences satisfying this condition. All right? Everything's okay? For the third one, I think I need to go to the next page. Now I'm going to construct a bijection between binary sequences and shortest path. How? So we have A1 ... AN. This will correspond to the ith step is up if AI equals 1 and down. Oh, sorry. Up, or we go either up or right if otherwise. It's best if I draw a diagram or an example. So 0, 1, 1, 0, 1. This corresponds to a lattice path like this. So let's write it. So it starts from 0, 0. It goes either this way or this way. Okay? So 0 means we go to the right, like this, one step to the right. Okay? 1 means we go one step up. 1 means we go up. 0 means to the left, to the right, and then. So this means 0, 1, 1, 0, 1. Okay? Do you see that this is a bijection? If you know this, yeah, like I labeled these steps, you can immediately see that it's a bijection. 0, 1, 1, 0, 1. What is the position of the ending point here? Something, comma, something. So the x-coordinate will be the number of zeros, which is n minus r. Y-coordinate will be the number of ones, which is r. Okay? So this proves the third statement. And corollary here, of course, this is very useful. Number of shortest path, simply I'm going to say path from 0, 0 to a comma b is what? A plus b comma a. Okay? So number of path from 0, 0 to a comma b like this. Number of path like this is a plus b, choose a. All right? So it's very useful to remember this. Yeah. Because sometimes it's easy if you use number of just R subsets, or sometimes it's more suitable if you use binary sequences, or sometimes it's better if you use shortest path. So it's it'll be very nice if you remember all of this. Okay, now let me talk about this Catalan number. This is an interesting number. So we know that number of paths from 0, 0 to a comma b is a plus b choose n, choose a. But we want to do something else. Number of paths from 0, 0 to n comma n. If I stop here, then the answer will be 2n choose n. But we want to do this, which never go below the line y equals x. So this number is 1 over n plus 1 choose 2n choose n. 1 over n plus 1 times 2n choose n. So this number of paths satisfying this condition is equal to this. This is called the Catalan number. This is very interesting number which appears very often in combinatorics. Okay, so for example, I think this is the path, this is the line y equals x. We want to compute number of paths that stays on or above this, like so something like that. We want to have this path that never goes below this line. So we don't want, this is good, but we don't want a path like that goes below like this. This is bad. We want to compute number of a good path, meaning good means it never goes below this line. So of course, this number will be smaller than, the answer will be smaller than this, because this is the total number of paths from here to here. We want to compute a good path. All right, so let me prove this in the next page. The proof. So the total number of paths from 0, 0 to n, n is what? 2n choose n. We know this. And let's say Gn is the number of good paths. Good path means, stays on or above this. So basically, this is the number we want. We want to know Gn. And let's say Bn is the number of bad paths. So bad path, if some path is a bad path, then it has to go below this line y equals x. Okay? And there's a nice, what do we know there? we know not much, but at least we know Gn plus Bn is the total number of paths. So this, okay? This is for sure. So finding Gn is equivalent to finding Bn. If you know Bn, you know Gn, and vice versa. And in fact, we will compute Bn instead of Gn, because bad path, number of bad paths is easier to compute. There is an interesting argument to prove to compute the Bn. And you can have this observation. A bad path always touches the line y equals x minus 1. So let's go back to here. So this line, let's say, this is y equals x, right? And this line is y equals x minus 1. As you can see, it touches here. It may touch several times, and it may go below, even below than this. But what we can be sure about is that a bad path must touch this line, right? Is this clear? Can you believe me? You know, it's very simple. You have to believe me. Okay, so what do we do with this? So I'm gonna this is the line. So here it is n comma n. This is the line y equals x. Let's say this is the line y equals x minus 1. Okay? So we have a bad path that goes something like this. So this is an example of a bad path. Let's say this. Okay? So bad path. It may touch this several times, but at least once. So let's say P. First point, touching point. Okay? You may have several touching points, but just find the first touching point. Okay, now what I'm going to do is I'm going to reflect the first part from 0 to P about this line, y equals x minus 1. Flip this about this line, like a mirror, that we get this. Okay? Do you see? I just flipped this part along this line. Then what is this point? What is the starting point? You flip 0 to 0 about this line, then you get minus 1 comma minus 1. So the starting point is 1 comma minus 1. Okay. Now, so let's say L is this path, bad path. We have L, bad path L. Let's say L prime is the path that is this. What can I say? I'm going to say L prime is the path obtained from L by flipping the first part about this line. Do you see? The blue is bad path L. L prime is the one obtained doing this. Okay. Then L prime is a path from 1 comma minus 1 to n comma n, right? As you can see, from here to here. And any path from 1 comma minus 1 to n comma n will touch this line. It has to touch because, you know, this is only, they are in the different sides of the plane divided by this line. There can be many, but it must touch at least once. So again, you find the first touching point, and if you flip this, you will get the bad path back. So this is a bijection. So this gives a bijection from bad path, send bad path to all path from 1 comma minus 1 to n comma n. So the number of bad path is equal to, this is 2, is equal to number of path from this point to this point. But number of path from certain point to certain point is always easy, just a binomial coefficient. So what is the number of bad path? So what is Bn? Number of path from here to here. That is, this is not the origin, but all you need to do is to find the length here and length here. So this part is what? N minus 1, and this is n plus 1. So this is basically the same as number of path from the origin to n minus 1, comma n plus 1. This, or the same thing as this. But we know what this is. So if, maybe I don't need the space. So Bn here, you can see, is some of them is 2n and n minus 1. Okay? That's basically it. Now Gn is, okay. So Gn is 2n choose n minus 2n choose n minus 1. But this, if you can compute, you can see that. Why? Because 2n, this is 2n factorial, n minus 1 factorial, n plus 1 factorial. But this is, n factorial, then n minus 1, we have to multiply. It's like this, right? Because if you cancel this, we get n minus 1 factorial. And if you combine these, you get n plus 1 factorial. So if you substitute this over here, then you get this number. Okay? That's the proof. So the Catalan number is the number of path from 0, the origin to n comma n that stay on or above this line y equals x. And using this kind of argument, reflecting a path, we can find the number of bad path, and that's it.